Right. Now, in terms of so for now, I'll just say a few things about sequences and series. So, regarding sequences and series, a sequence is a list. A series is the sum of the numbers in that list, right? So, for example, here's a sequence. 1, 2, 3, 4. That's probably the most basic sequence you can think of, perhaps. Yeah, this is the sequence that you learn in kindergarten, right? Just how to count. So this is your most basic sequence. A series almost looks like a sequence, except instead of these commas you have a plus. And so you can see how in this, if I express a sequence or a series in this form, I'm going to show you at least enough terms, right, so that it's self-evident what the pattern is. And when it's self-evident what the pattern is, I can put this dot, dot, dot. In both of these cases, I'll refer to each of these as a term of the sequence or a term of the series, right? So like the 3 is the third term of the sequence. Some other notation that we're going to be using pretty frequently is sometimes I might refer to this as A subscript n, right? And what I mean by that, let's see here. What I mean by that is this. I'm calling the sequence. This is the sequence that I'm naming A. And the subscript tells me which term I'm looking at. So in this case, I can see that A sub 1 is 1, A sub 2 is 2, A sub 3 is 3, and so on and so forth. So if I have, well, I'll just talk about this for now. That's my sequence. When we talk about a series, right, then we're kind of asking like, what happens if I add these all up, okay? In this case, you can see how this series, well, what does this series add up to? Yeah, I think your intuition would serve you well. It seems like it's just going to keep getting bigger and bigger and bigger without bound, and it does, right? So what we say in this case, you could say equals, it's going to take a little while for the ink to start flowing, equals infinity, right? But we would say this sequence, this series, diverges. Yeah, the screen pin isn't working so well, but this series diverges. The series that we're particularly interested in this class are the ones where the series converges, right? So this one isn't especially interesting to us. But yeah, so when we look at, I think it's 5.1 and 5.2 for the homework. Let's see here. Yeah, 5.1 and 5.2. 5.1 is all about sequences from the book. 5.2 is all about series, okay? And so, right. So yeah, so here's some examples of series that we, I thought maybe the best way to start looking at this is to, I thought a good way to look at this is to just give you like the 3 basic examples of series. So let's do this one. 1 plus 2 plus 4 plus 8 plus 16. Let's think. Actually, I want one that actually converges. Actually, this one doesn't converge. How about this? 1 plus 1/2 plus 1/4 plus 1/8. Can you see what the next term would have been?
37.
Yeah, that's right. So the denominators just keep doubling, right? Another interesting series is this one. Starts off the same, all right? But the pattern is different. What's the term that comes after this one? Yeah. This one is another interesting one. And then the other case, and I think this is probably this next example, I think, has a little bit of a historical background to it, which might provide some of the motivation for this whole topic, right? Because this was an open-ended question that wasn't answered for some time. Can you see what the next term would be in this case?
37? 37? No, 32. Because that's
Yeah, somewhere in between.
35. 35. So 5. Oh, 36. My bad. Plus
Yeah.
11. I had that wrong.
Oh, I see what you're thinking. I see what you're thinking. Yeah, you're thinking, what do I do to this number to get to that number? Yeah, I'm thinking something even simpler. Think of this series as coming from this series.
Squared.
Yeah, 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25. Yeah, so this one is, this one was kind of an open-ended question, and like, you know, Euler is the one who finally answered this one, right? But it turns out, notice that in each of these, as you move down the line, the terms get smaller and smaller and smaller. And it turns out that 2 of these 3 converge. 1 of the 3 doesn't converge. Surprisingly. But I think these are 3 important series, and as we look at more and more different scenarios, I think it's, for me, the way I see this stuff is like analogous to one of these 3 cases. Okay? Now, to answer, the easiest one to deal with is the first one. This was called geometric. Series. Right? And the next one is called a harmonic series. And I don't know if this has a name. It's just a series of sorts. And you know, at the beginning of like integral calculus, we started talking about sigma notation. Well, we're going to be returning back to that, okay? So very often when I want to refer to one of these series, I'm not going to write it this way, simply because it just takes more time. It's a little more compact if I write it like this. With sigma notation, right? Remember how that works? What would I?
Starting points and everything like that.
Yeah, so like, I don't know, let's start with the middle one, the harmonic series, right? How would I fill in? I need to put something here that indicates where I begin. Something over here, yeah, and I needed some sort of an index. So like I equals 1. What else? Yeah, and because of that dot, dot, dot. Huh? Yeah. Anyway,
Wait, and that's an N on top.
yeah. Actually, what we're going to do is we're going to put just infinity to say that you don't stop, you know. And then the pattern here is going to be 1 over I. Right? Yeah. And like in this case, right, what would this one be?
I, 2i. I mean, same thing, I equals
I squared.
So I equals what? 1? Okay.
Oh, well, 1 over 2i. Yeah.
Ah. Yeah, it's kind of like even numbers.
Yeah.
That would work.
That
Let's
is
see
one
here.
for 1.
Yeah, notice that like if I equals 1,
Oh, yeah.
then that means we're starting at 1/2. When I equals 2, we'd get 1/4.
Yeah.
And when I equals 3, we get 1/6. And we need to jump past 1/4 to 1/8. You know what I mean?
So I squared.
Yeah.
Or no, 2 to
Mhm.
I.
Yeah.
But then
Because these are all powers of 2. In fact, you could think of it like this. 2 to the 0 power. 2 to the first power. This is 2 to the second power, right?
Yeah.
This right here is 2 to the third power.
So your index has to be 0.
Yeah. So we're instead of starting at 1, we're going to start at 0, right? And that's going to be 2 to the I power. And we just keep going forever. And for this in this third case, how would we express this?
I to the I.
Well, I think you said it a moment ago by accident,
There you go.
right? I was just taking this and squaring it, right?
Right.
So this becomes 1 squared, 2 squared, 3 squared, right?
Yeah, okay, yeah. I to the square.
Yeah.
No,
So we're going to start.
no. Into the
So I'm starting where?
1
Uh-huh. But the pattern here is 1 over.
into no I to the square.
Yeah. We just keep going forever. So these are the 3 cases that we're interested in. So with these 3 examples, I'm jumping straight into 5.2, having to do with these series. The reason why it's important that we get good at sequences and understand what's going on with sequences is so that I can make sense of this. So what really does this infinity mean? It means that in each of these cases, I'm thinking of each of these series as a sequence of partial sums. So for example, if I let's say I take so this is a series, and this series is a sequence of partial sums. And by that I mean this. It means that I have in mind a list of numbers, right? And the sequence, I'll call this sequence B, right? Bn.
Yeah.
That's going to be the sum from I equals 0, not to infinity, but to n, of 1 over 2 to the ith power. And this right here defines a sequence, right? So for example, if B0, what is B0? It's the sum from I equals 0 to 0 of 1 over 2 to the I. That means there's only one term. I'm starting and ending at the same place, right? And yeah, you said 1, right? Yeah, that's right. Because 2 to the 0 power is 1. So the first term in the sequence is 1. How about B1?
Oh, sorry.
Yeah. starting at 0, ending at 1, but according to the same pattern, right? Yeah, I think you did some arithmetic in your head. It's literally 1 over 2 to the 0 power plus 1 over 2 to the first power.
Oh, when you were asking, you wanted me to say that, not.
Whatever.
Okay.
Whatever you would have said, I would have asked the other question after that. Yeah, so you can see that this is, you do a little arithmetic, and you can see this is just 1 plus 1/2, also known as 3/2, right? And so this is the first term in my sequence. This is the second term in my sequence, right? The third term, or b sub 2. Maybe I should refer to this as the 0th term of my sequence, just so. First term, second term. It's going to include these first two terms already, with one additional term, right? So it's literally 1 over 2 to the 0 plus 1 over 2 to the 1 plus 1 over 2 squared, right? But we've already done the hard work of evaluating the first two terms. So I would just think of it as 3 over 2 plus 1 over 4. Get a common denominator, I think you get 6, 7/4. And you start to get a sense of how this sequence is growing, right? If you're at as you can see on a number line, if this is 0, and this is 1, and this is 2, it looks like the first term of my sequence, or the sequence of partial sums, starts right here. But then from there I add 1/2 to that. So I get 3/2 or 1 1/2, right? And then I add 1/4 to that. So now it's right there. See what's happening? So if I were to add on the next term, B3 would just be this number plus 1/8, which is really just half of the distance it is to 2, right there. The next term after that would be 1/16, which is just half of that remaining distance. Should be right there. And as you can see, as I just draw the number line, you start to see like the overarching pattern, right? Mm-hmm.
But isn't this the analogous to the whole Achilles of turtle?
Yeah, it's also known as Zeno's paradox,
Yeah, that's
right? So I think Zeno's paradox. So yeah, that was a paradox until calculus came around.
Yeah.
Now we don't consider it a paradox anymore.
I thought with physics would be quantum, but go ahead.
Yeah, that's true. But yeah, it's the idea is like the paradox is just like, does it ever actually get there? You know what I mean? And so in this class we're going to say yes, because otherwise I can't evaluate my sums. The sum is what you get when you get there.
So then this time is for limit?
Yeah.
Okay.
Yeah, exactly. So yeah, so at each iteration, right, we're just kind of getting closer and closer. And so you can see how when I'm evaluating a series, when you see that infinity, it's whenever anything isn't clear, we're going to reinterpret it as a sequence of partial sums. And then something in between, like these computations and this, number line, you might be able to get some intuition to help guide you through the solution. So, anyway, I think what I'd like to do now is kind of talk about how to evaluate this sum. I think when we start getting good at this stuff, you're gonna find that you're gonna be really grateful when you see something like this, because this is in the grand, when we get through this course and looking back, these will be the easy ones. You know what I mean? The techniques that I don't even need calculus to evaluate this sum, right? This actually could have been talked about in pre-calculus, right? Even this sum, I don't need calculus to evaluate this one, right? So we'll see. Yeah, actually, I don't think I need calculus to evaluate this sum either. So somewhere in there, there's some calculus. I think. Well, we'll see. All right, so for the geometric series, so what all geometric series have in common, right? Oh man, I should stop using this green. It doesn't even erase. What every geometric series has in common. So it looks something like this. So the first term is 1. The second term is, I'm just going to call it R. R for ratio. Because the next term, what makes it geometric is that...
I'm sorry, R for what?
Ratio. Ratio.
Ratio.
Yeah, R-A-T-I-O.
So it's always like a fraction.
Yeah, could be. What happens is like, so for the next one, is R squared. So every term is R multiplied by the previous term. You see what I mean? So the next term after this would be, yeah, this is called a geometric series, right? So you can see how this is a geometric series where R equals not 2. It'll become a little more clear if I write it like this.
R equals 1/2.
Yeah, R equals 1/2. This is 1. This is 1 times 1/2. And 1/4, you could think of that as 1/2 times 1/2, right? And this 1/2 cubed, it's the same thing as this term multiplied by 1/2 again, right? This term right here is the previous term multiplied by 1/2 yet again. So in that, notice I've already covered at least 3 different ways of writing the same series. So part of the difficulty of this class is spotting it and maybe putting it into the preferred form for whatever you're doing, all right? So yeah, so this is a geometric series with R equal 1/2. But in general, if I want to compute a geometric series, I'm going to kind of show you where the formula comes from, but at the end of the day, you just need to know the formula. Okay? It's a clever trick. It's a clever trick, I'd say. What I'm going to do is I'm calling the sum S, and I'm going to multiply both sides of this equation by R. So look what happens if I multiply this S by R in the right-hand side of this equation by R. I'm going to write it like this. SR would equal, if you distribute the R through each and every one of these terms, what you end up with is R plus R squared, R cubed, like that. It looks very similar to the original series. In fact, almost all but one term matches, right? See how the R here matches the R here, R squared and R squared, term per term. So the next time I'm going to try and exploit that that relationship by using subtraction. What you see is this, is as I add these up. So let me just write this down again. before I multiplied by r. If you take all these terms and subtract all these terms, if I line them up term for term, this minus this is 0, this minus this is 0, and all the way on down the line, no matter how far you go, they all cancel. And all I'm left with is what? Yeah. Let's see here. Yeah, maybe I should have subtracted in the opposite order, but since I'm taking this minus that, you'd be left with -1. I think if I thought ahead a little more, I would have subtracted the other way around. But no big deal, because at this point, I can now see that I have this.
Okay.
Yeah?
I got you. So we start off at the top.
Yep.
And then we multiply it on both sides.
Yep.
I got rid of the 1 plus r plus r squared. So we now r plus r squared plus so forth.
Mm-hmm.
So then on the next line, we subtracted the third equation for the
Mm-hmm.
equation.
Mm. Yeah.
So, no, so we subtracted the original equation from the third equation.
Mm-hmm.
That gives us like, but, okay.
Yeah.
The SR is not like y equals, it is y equals, it's not like this equals 0. Gotcha.
Mm-hmm. Mm-hmm. Yeah, is that okay?
It's a body.
Yeah. And let me just say one more thing. I just made a big fuss about how a series is really a sequence of partial sums, right? And we make sense of it by rewriting it as a sequence, you know? Perhaps a better argument than what I'm giving you here would be to not use the ... but actually treat it as a sequence of partial sums. And then because I think I'm requiring you to make a pretty huge mental leap here. You know, just trusting that what's going on with this ... is pretty clear. But the way we make it crystal clear is I would reinterpret this as a sequence of partial sums and do this properly, you know. Another question that we're going to be interested in this class is under what circumstances does a series converge, right? It turns out that for certain values of r, this will add up to what I'm about to write, but for other values of r, it won't. It depends. You remember how I started to write one thing, but then I stopped myself? I started to write earlier this. When like 15 minutes ago or so, I started writing 1 plus 2 plus 4 plus 8, right? Notice that this is also a geometric series. Each term is 2 multiplied by the previous term. So 2 times 1 is 2, 2 times 2 is 4, 2 times 4 is 8. This is also a geometric series, but this geometric series, it doesn't converge, in other words. Yeah. So I'm doing this work to kind of show, what the formula is, but this formula you have to use with caution, right? You have to use with caution because, so what I'm about to do is I'm about to divide both sides by r minus 1. So my formula is -1 over r minus 1. I think if you look it up in the book, they're going to write it in a slightly different form without a negative on top. If I multiply the top and bottom by -1, it becomes 1 over. It would be -r plus 1, which I just chose to write it like that, 1 minus r. Okay? So interestingly, if you return back to this example when r was equal to 1/2, this is telling me what the sum will add up to. It's saying that if r equals 1/2, Well, 1 minus 1/2, the denominator, is 1/2. And 1 divided by 1/2 would be 2. And it looked like it was going to add up to 2 anyway, right? See how the sequence was converging to 2? So yeah, so this formula works when r equals 1/2. But when r equals 2, like over there, if I tried to throw the same formula at that geometric series, that would be a mistake. Because if you do it kind of blindly, you'd be like, okay, well, if r equals 2, 1 minus 2 is -1. And I get 1 divided by -1, which is -1. And clearly this doesn't add up to -1, right? So this is a formula that you got to use with caution, okay? What I really need to include in this box is a sentence that says where r, there's some condition.
Less than 1?
Yeah, less than 1. But yeah, would that include like negatives though?
No, less than 1 and positive. Between 1 and 0?
Yeah, that would be true. That would be sufficient or necessary. That would be true, but there's more. It's actually a little more than that. The negatives are okay as well. Down to -1.
So, okay, between 1 and -1.
Yeah.
That's a fraction.
Yeah. So yeah, so I think what I'm going to do, actually, I wasn't planning on it, but I'm going to go ahead and, it would be a good review of 151, where we did the limits, right? Because I think when I look at it from that perspective, you're going to see, you'll be able to see a little more clearly. Yeah, I think from that perspective, if I regard this as a sequence of partial sums, you'll see a little more clearly what the condition is. And this is arguably the most important part of the formula, right? It turns out the way you're gonna see it in the book is like this. Right? So notice that by writing it this way, I'm allowing for r to be negative, right? So I'm going to be like more or less repeating myself. It's pretty much the same argument, but with a little more precision and without using the ... Right? Yeah.
Quick question.
Mm-hmm.
So you said every geometric series has that
Yeah.
R.
Yeah.
And is it safe to assume that every time we see a geometric series that pretty much like the second term
Mm-hmm.
is R?
Sometimes you might have to be a little more clever.
So to define the pattern.
Like, for example, how about this one? 100 plus 20 plus 4
Okay.
plus 0.8.
So 1/5.
Yeah. So this is something where, you know, we're going to use that formula, but we have to do a little bit of algebra first to make it work, right? So notice that this formula only works if I'm starting with a 1, and this doesn't start with a 1, right? So, yeah, I think what I would do is I would probably, like, if I was to factor out, yeah, but because you notice that this is 1/5 of 100 is 20, and 1/5 of 20 is 4, and 1/5 of 4 is 0.8. Then yeah, this is a geometric series, right? But what I'm going to do first is I'm going to factor out a 100 out of all the terms. So now the first term is 1, and the second term would be 1/5 of 100. The next term would be
you're saying basically is make it to where we
Yeah.
All right, right.
Exactly. So yeah, so there is this crucial first step right here, right? And then now with that, just applying the formula, and notice that now that it's clear that the ratio is 1/5,
Right.
and the absolute, and that 1/5 is less than 1, right? As my condition requires, I can go ahead and say times 1 over 1 minus 1/5. Yeah, I guess. Yeah. That'll be 4/5, and 1 divided by 4/5 is 5/4. So yeah, 500 over 4. I guess 4 is in 125 times, so 125. Turns out if you keep adding these things on, actually it almost looks like it, right? 100.
Oh, yeah.
The sequence of partial sums, see how this stops at 120? 124, 124.8. You know what I mean? And so, yeah, it looks like it's kind of getting close to 125. But we didn't really know for sure until we did this sort of use this formula. So yeah, so this is a case where it is a geometric series, but, you know, we had to kind of put it into this form before we could use this formula. Well, let me just take a look at this real quick. All right. Yeah. Let's see here. We got this and that. Yeah, I guess it's a good time for a break. Yeah.
I can argue.
Right. So, yeah, I was just saying that I wanted to kind of repeat this argument, okay, but with a little more care. I don't know, maybe I should have done it with more care to begin with, but yeah, at least the second time through, it'll be a little more familiar where I'm going with it, you know. So, what I want to do, when I kind of, you know, put this up there to show, like, sometimes you have to be somewhat versatile, in that not every geometric series will look like that. Like, for example, this one starts with 100, not with 1. So I just simply factored it out, and then now it looks like something like that. But anyway, I'm going to try and, I want to repeat the argument I did here, but I'm going to treat this series like a sequence of partial sums. Okay? So what I'm going to do instead is I'm going to say this. S is going to be 1 plus r squared plus ... but it's going to stop. Okay? It's going to stop at r to the n, let's say. If I have, now this is also called a geometric series. A series doesn't have to be infinite. This is a finite geometric series, okay? Because it has a stopping point. And in this case, I'm pretty much going to use the same argument, right? I'm going to take, I'm going to multiply both sides by r. And when I do that, you can see that I get again, distributing just like I did over there. What would the last term be?
R to the 2n?
Yeah.
Close, but not 2n. This is r to the first power, right?
Right.
So when you multiply those together, you're adding the exponents.
So r to n plus 1.
Yeah. All right? For the whole internet to know. But yeah, you can see how now, maybe I can save myself one step. Now that I have a little more foresight, I'm going to take this left-hand side minus this left-hand side, and I'm going to take all these terms minus all these terms, right? So S minus SR. So I'm looking at these two equations. That means I'm taking this one has nothing to subtract from it. But the R minus R, that's going to cancel. The R squared minus R squared is going to cancel. The next term that's not written here is going to cancel with that one. And the Rn is going to cancel with, does it have something to cancel with?
No. I would say something.
Yeah, so you got to bear in mind that when I write this dot, 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 I'm implying that everything that which comes after R cubed is there. But I'm also implying that everything that comes before each of these is there, just not written. So like the term just before this one is R raised to what power? Mm-hmm. And the term just before this one, so actually this term is going to cancel with the second to last term here. The only thing but this guy has nothing to cancel with. You know what I mean? Yeah. It would have canceled with the next term if I had written it, but I didn't. You see what I mean? So what I'm left with is that. Everything else canceled. This is actually an example of a telescoping series. When a bunch of stuff cancels, we call it telescoping. So again, just like before, solving for S. My ultimate goal is to evaluate that sum. I can now say that S is equal to 1 minus